you kind of accept, and what is not there, you drop. That's the whole idea of an Internet Routing Registry database, right? So it describes route origination. This particular prefix is allowed to be originated out of that network, right? So it's pretty straightforward, right? The only problem with this is, so what we normally do with IRR is we use what's called this RPSL tools, routing policy specification language tools, to automate filters. Let's say I'm peering with ErthamNet. So I'll point my RPSL tool to the IRR database, where ErthamNet would have created all the Route 6 objects, and then that tool will automate the filters. It will accept what's in the database, it will deny what doesn't exist in the database, right? Concept is straightforward, but there's no single authority model when it comes to IRR, right? So here are examples. The first example, I'm using a tool called BGPQ3. This is a V4 prefix list in Cisco syntax by default, Cisco iOS syntax. This is a V6 prefix filter. Here is what I try to do for BIRD, the BIRD routing protocol, right? This is the V4 prefix filter. This is the V6 prefix. It's pretty straightforward. It helps you automate things, right? Easy, straightforward. But how do I trust whether this filter is correct or not? Yes, it helped me generate this filter, but what if the entries in the database are not correct? Okay, my RPSL tool has generated the filter, so I should, those days in BT, we generate the filters and I would still manually verify just to be sure that the database entries are not incorrect, right? So the problem with IRR is this, there is no single authority model in IRR, right? There are so many IRR databases. So with regards to the single authority model, how do I know if IRR entry is genuine or not? What does that mean? If you look at IRR databases like RADB, try looking up one prefix and you would be surprised to see 5 or 6 entries for the same route. So which one is correct? Some people forget to delete their old records. You're an engineer, tomorrow you leave your network, somebody takes over your network, you didn't delete the old records. So how do I trust whether it's correct or not, right? That's the problem. There are about 25 IRR databases. So which one do I trust? Which one do I pick, right? RADB has one, every big ISP runs their own IRR database, right? So which one do I trust? And incomplete data, what does this mean? The fact that we use the IRR database and entries there, we accept. So that means, what if there is no entry there? Does that mean that the engineer did not create the entry, or the route really does not exist, right? I need to be able to verify that. And there is no way I can verify that using the current IRR database. Sometimes I'm just too lazy. I may not be creating an entry in IRR database. But if people use this to filter routes, they would filter my routes out, even though I have a genuine route, right? So with all those history, all those background, and all those limitations in the tool, let's go back to basics, right? Remember, we said since we can't identify what is bad, let's try and identify what is good, right? So that's where the idea is. So then people in the industry, people like Randy, people like Jeff and others, they thought, can we try and identify what is good at least, right? So can we use digital signatures? Example, let's say you are my upstream, you are announcing my route, somebody receives that route. How do that person know that I authorize you to announce that route on my behalf, right? So can we use digital signatures, right? To authoritatively prove that, let's say I announce my route, someone somewhere in the US receives that route, they need to be able to authoritatively track that up the chain of trust and say, okay, Tashi did authorize that network to announce that route. That network is not hijacking that route. So let's try and use digital signatures for that, right? So the idea is we'll again use public key cryptography, right? I'll use my private key to sign that authority, it's digital signature, right? Whoever receives that route can now verify that authority using the chain of trust, right? Let's have a look how that works. But the problem with any thing associated with digital signatures is you need a chain of trust. So how do we build a chain of trust? With names, there are just too many certificate authorities. But with numbers, there are only 5 RIRs, right? It's the RIRs who delegate addresses down, right? So it's straightforward. So RIRs delegate addresses either to N network operators or to NIRs, National Internet Registries, who delegate it further. So the chain of trust actually follows the delegation hierarchy, right? I think I need to update this bit here, but it explains, right? So example, APNIC as a registry delegates, let's say, a /32 IPv6 prefix to operator here. Along with that delegation, APNIC also issues a resource certificate, right? That resource certificate is nothing but APNIC's root signing your public key and giving it to you, right? And now using that resource certificate, you can start signing any authority that you want, right? So that's the whole idea. Whenever an address or a resource holder delegates resources to anyone, you also issue a resource certificate, so you get the address plus the resource certificate, and now using that resource certificate, you as, let's say, Mobicom can authorize any network globally and say, all right, entity, go ahead, announce my route to the internet, right? You can digitally sign that, so that when I receive that route, let's say in Brisbane, I go, okay, that's Mobicom's route, it's coming out of entity's network, let me go and trace that back up the chain of trust whether Mobicom authorized that or not, right? It's very simple. Conceptually, right? So in routing language, it's nothing but a route origin authority, me authorizing a particular network to announce my routes, right? Here is an example. You have a /19 prefix here, right? That's my prefix. You specify up to what length, up to a /24, and you are saying this network AS17660 is allowed to announce this route. Right? So that is what we mean by route origin authority. And how can we use this digitally signed object? We are all engineers. We are used to filtering routes. We create prefix filters, AS path filters, this filter, that filter. So using ROAs, we can also start filtering routes using ROAs now, right? So everyone creates their ROAs. Anyways, you create your digital authority, right? That gets published. Since APNIC is your registry, APNIC pushes that to the APNIC and the global RPK repository. You run a validator tool, a relying party tool, right? Which fetches all these ROAs globally and maintains a validated cache. The beauty is cryptography stops here. There's no cryptography towards my router. The cryptography is up to the validator. So the validator strips the cryptography, sends me a copy of the validated cache to my border routers. My border routers talk over a RTR protocol, right? So my now router has a cache of the validated ROAs. So whenever my border router talks to some other network, and that network, let's say in this example, that network is announcing a 2406.6400/48, it comes to my border router. Before I accept that route, I go, hold on, let me look at the ROA database, the validated cache. I see that prefix, I see it's coming from that AS, I look at my validated cache of ROAs. And I look at the ROA and I go, okay, the prefix matches 2406.6400, and the length is a /48 that I'm receiving, but my cache shows a /32 to 48. It's within the range. Now let me check the origin AS. The origin AS, it's coming from AS 17821, and my validated row cache shows origin AS is 17821. It's a valid route. Then only I accept it into my BGP table and into my routing table. If any of this does not match, if the prefix is wrong or the length is not right, let's say I have a ROA only a /32. Somebody is trying to hijack my route with more specific, it'll come here, it's invalid. So you will drop that route, right? So it helps this kind of misorigination or route hijacks. Okay? So this is what we mean by route origin validation, right? But is that the perfect solution, right? How difficult is it to spoof the source AS? I could be spoofing anyone's source AS, right? If I'm somewhere in the middle, I could spoof Mobicom's AS and announce your prefix to the world. And they go like, oh, ROA origin AS is right, the prefix is right, the length is right, it's a valid one. but instead of traffic going to the original, I'm in the middle, I receive those traffic, right? So that means route origin validation alone is not good enough, right? So you need some form of validating the path also of the routes, right? And the way it works is you form a chain of signatures, right? Me in AS1, whenever I announce something to my next neighbor AS, I sign the path, right? And when my neighbor AS2 wants to announce that further onwards to AS3 and AS4, they sign that announcement on top of my previous signature, right? So if AS3 was to validate the validity of this announcement, they would of course first check that there is a valid ROA existing for that. If the origin AS and the prefix length and everything matches, then it will try to validate the AS path validation, right? Great idea, simple idea, but it's a big problem, right? Because with route origin validation, there is no cryptography involved on my router. The cryptography is on the validator. With AS path validation, cryptography comes heavily onto the routers. That means my routers become more expensive. The vendors would be so happy, right? Because then they can sell you expensive boxes. And there is no clear-cut mechanism. How do I distribute keys to every router on the internet? Right? So that's why, while the idea is good, there are no known implementations of AS path validation, at least in operational networks, right? But do we just say that, oh, since route origin validation is not good enough and AS path validation still doesn't work, I'm not going to do any security work, right? So it's saying that you'll wait for the perfect solution and you won't do anything until then. Don't do that, right? We have route origin validation. We have other filtering techniques. You don't have to wait for the perfect solution to happen, right? So what can we do? Right? We can follow basic hygiene, RFC 7454, BGP best practices, security best practices. How about RFC 8212? BGP by default is a very leaky protocol, right? Let's say if I'm configuring two BGP sessions parallelly, if I bring this session up, my BGP will start leaking this network to this particular peer without me even telling it to do it. BGP is leaky. So this RFC proposes that to prevent route leaks, it says, until I explicitly tell BGP to announce that route, it's not allowed to announce, right? But the problem is not many operating systems support this router operating system, right? So you have to wait for vendors to implement. So I tell people that you don't have to wait. You can come up with different hacks, right? So instead, my suggestion would be when you are configuring your BGP peering, first shut down your BGP, create your filters, apply your filters, then bring up your BGP so there are no leaks, right? And of course, filter, create prefix filters, create prefix limits, right? Create AS path filters, and most engineers already know how to do this. But why are those big networks not doing? Why do we keep seeing leaks after leaks every month, every week on the internet, right? And most importantly, please create your ROAs. Then coming week, we will be running a ROA signing social, right? So that would be day four of the workshop. We will be doing a ROA signing social, so please come over there, right? We will help you create your ROAs, and you'll get a nice t-shirt for that. If not for anything, come for the t-shirt, right? And then once you have your ROAs created, start filtering things, right? And please join industry initiatives like MANRIS from ISOC, mutually agreed norms for routing security, right? And that should be it. Just to let you know, since February this year, AT&T has started dropping invalids, but only from their peers. Mark Tinker, CCOM, they made this announcement on April 1st. Everybody thought it was an April Fool's joke, so they changed the date to 5th April, where they started, one of the biggest transit providers in Africa, they started dropping invalids. Right. And in the region, Myanmar IX started, it's a 1-year-old IX, it's dropping invalids. Malaysia Research and Education Network, they're dropping invalids. It's straightforward, it's nothing difficult, right? And yes, acknowledgement. Thank you, Jeff. Thank you, Randy. Thank you so much, everyone.
Okay, do we have any questions from him? асуулт асуух юм байна уу? Ташигаас. Okay, cool. Hold on. Okay, thank you, Tashi. Now our next speaker is Hervey from NSRC, and he will talk about RNE strategy around the world. So welcome to the stage.
Testing, there we go. Excellent, thank you very much. I'm going to set up my timer so I don't keep talking for too long. Here we go. And let's see if this works. Good morning, everybody. Morning, hope everybody's doing well. My name's Hervey Allen. I work for a group called the Network Startup Resource Center, and I'm here to talk about some successes, strategies, and challenges with research and education networks around the world. Let's see if this will go forward. I think turning it on might help. I'll try it. Well, yeah. No light on it at this point. Wonderful.
This one is next.
Oh, that one's next, okay. Thank you very much. All right. So, basically these are the slides where I convince you that I have some idea what I'm talking about, with lots of text on them and some images of our organization. We do a lot of stuff that involves helping people build networks in emerging parts of the world, and we've been doing it for about 25 years. We are request-based and driven. This means we really try never to go in and tell somebody what to do. Rather, we wait for people to ask us if we can assist them, and then we assist as possible. Okay, so you can see this in our goal statement, which we put right on our website, all that kind of stuff. It's our driving philosophy of how we work. And we're kind of spread out. We have people all over the globe. They work with us in various capacities, and we have a home base on the west coast of the United States at the University of Oregon. That's where I am. That's what it looks like. We like our football team. It snows sometimes, and our mascot is Donald Duck. And over the years, since about 1991, we've been in or gone to around 120 countries, done about 1,000 separate activities, meaning workshops, helping people directly, providing equipment, giving advice, that kind of stuff, and trained probably around 50,000 network engineers. And these are rough numbers, but we're within sort of the range of what we've done. So before I get started, a few acronyms that you'll be hearing, and you'll probably hear this off and on today. A big one is R&E, Research and Education. This is our worldview. It's a little different than the commercial point of view. So a REN is a research and education network in general, a network designed to support research and education. You can flip that around and say education and research. An NREN is on a national scale, so like all of Mongolia, all of a nation, and a regional REN tends to be a group of networks in an area roughly defined that have interconnected their services. Frictionless, when I say frictionless, I mean network traffic that can pass through a start point and an end point without being interfered with along the way. So no firewalls, no filters that are going to drop packets. The idea is that the network itself, if it sees your data, and particularly if it sees a large data flow, tries to enable this. And that's a big piece that comes with research and education networks. So why would you want to have a research and education network? That's not really what this talk is about, but I will mention some of the key points. One of the ways you can, if you're interested in this and see why people say research and education networks are a good thing, You can just search for the benefits of research and education network, and you will read lots and lots of papers about this from various organizations like GÉANT in Europe and Internet2 in the United States, and TAIN or Asia Connect and many other places. So there are some benefits and there's some disadvantages, and oftentimes institutions will use both type of networks for their connectivity. So here's a few of the popular reasons why people build research and education networks. There are a lot, right? A big one is universities can get together, pool their money, and buy more connectivity. It's called a buyer's club. They can provide resources to each other and the people on their network. So software, cloud computing, compute, maybe publications, etc. You can become part of an authentication realm like EduRoam, so you can move between universities and other institutions worldwide and use your credentials at your institution to get onto the network. That's really nice. And you can get a bunch more complex connection advantages. So maybe your NREN helps you figure out how to dual home at your network, right? Get access to a local internet exchange point. Perhaps with the leverage of the size of your NREN, then you can connect to things like Google caches, Facebook, YouTube, all that kind of good stuff. Let your NREN do some of your routing security, help you out with voice over IP, video on demand, all that kind of good stuff, right? And you can get all of this from a commercial network as well. It just depends on your situation. You may get this a little more responsive to your needs, and it may be less expensive. And all of that depends. You might have some more control over your traffic when it comes to an NREN versus being connected commercially. And a big one is the direct connection to the global research and education fabric. So frictionless end-to-end connectivity for large data streams. This is fundamental if you're going to do research with large data. Absolutely mission critical. R&E networks are optimized to allow this. Commercial networks are generally optimized to try and stop that. Not wholeheartedly, but if you see a very large data stream on your network, oftentimes it looks like an attack. It will be throttled. It makes total sense from a commercial point of view. So let's just very quickly look at how much fiber there is on the planet as we try to build these networks. This is a very general view, but there's a lot of fiber that's going through the undersea cable systems now and landing all over the planet. Then there's a bunch of global NRENs, and if you look at them, you'll probably figure out, oh yeah, they're probably using that fiber, right? And there's all sorts of different ways they gain access to it. And then people build these very large research and education networks that have viewpoints from different parts of the world. So here in the Asia Pacific, we have an Asia Pacific backbone, and a lot of different global RENs or regional RENs participate in it and have connectivity to the Asia Pacific backbone topology. GÉANT has a very European-centric view. Traffic tries to come back to them, right? Internet2 in the US, traffic tries to come back to the US. And then you have some of the regional RENs, and there are many, but I'm just going to show you a few. And GÉANT supports quite a few of them. So one of the things mentioned today here on the Asia Connect is, if you'll look, of course, the dotted line up to Mongolia, right? And that's an access into the global R&E fabric straight through the Asia Connect initiative, which is supported by GÉANT. And then your traffic can actually, once you get onto this network, hop onto networks like the US and places like Singapore and Japan, and get onto other networks as well. And all of that is optimized for your traffic to flow for research and education. It has a different viewpoint than going commercially. And then once you get somewhere like Europe, you get into these networks where you have access to everything very quickly. Same with South America. Note that GÉANT connects directly here, right? So if you can get to Europe, you can get to South America. That's one route, or you can go across the Pacific. And then there's just a lot of fiber, okay? A lot of fiber. And we can always use more, but it's there. This is a big change in Africa. There's a lot of terrestrial fiber now in Africa. United States, of course, lots of fiber. So they're there, the resources are there, but what keeps us from actually building these networks, right? There's a lot of routes on top of this infrastructure. The fiber is owned, leased, or under contract to various R&E groups. So what gets in the way of building a more robust, functional research and education networks to help support the global efforts of education and research, particularly across countries and researchers? A bunch of challenges that we've run into over the years, and some of these include, and this is just from experience out in the field, big one, of course, is lack of accessible bandwidth and competition between your service providers. Lack of stability in some regions. Power is a big issue for that. Challenges with navigating all the administrative bits of becoming an NREN, getting your network space, getting your ASN, all that kind of stuff. When you first do it, it can be hard. Network security issues and other infrastructure items, air conditioning, dust, moisture, cabling, people. There's just a lot that goes into building a robust network. And we run into these challenges. And they exist everywhere, right? In all countries worldwide. Lack of terrestrial fiber, that makes a high-speed research and education network difficult. And then the challenge of getting access to the fiber that may be there can be tricky, because perhaps it's only on a commercial network. And whether or not you're going to be given that access at any reasonable rate generally is an issue between the possibility of your research education network and your local government. Not always. Trying to get equipment in to a country with high import duties, taxes, charges for storage. Some countries allow equipment for educational networks in tax-free, others don't. The situation's kind of gotten better over the years, but it can still be very difficult. And some of the environments in terms of regulations about whether or not you can get access to the networks in your country for research and education, that can be tricky as well. Okay, another big issue that we run into is, so you finally build your network, it's finally being delivered to your campuses or your educational institutions, but it turns out those networks actually aren't very well built, and that's often because they've never had good connectivity. So we see this a lot where you go to a university, and suddenly they've gone from their 50 or 100 megabyte connection to a gig, or maybe even faster. But the researchers say at the end of their network on the edge, they don't really see a difference. This is fairly common. So why do we care about that? Well, when we get to all these national, regional, and global networks, the first connection's down on the campus, and it's with your people and your researchers. All the traffic that flows across all these wonderful networks we build starts down here. So if it can't get out, if it can't even start, then the network you built will be less successful. So a typical issue we see, just to digress a little bit, some sort of network where everything has been daisy chained. You have a connection to the outside world here, right? And it comes in, and unfortunately, rather than distributing it across a few routers, it's been daisy chained across multiple switches. The more switches you put into a path on a network, eventually, the worse your performance will be. So you can go out and you can get some organization by routing in the core and breaking your network up in the segments. That helps tremendously. Oftentimes it involves putting a little fiber in your local area, stuff like that. And you get a final network design, which is sort of the traditional campus research institution design that includes abilities to pass large data sets in a frictionless manner. And the big piece, if you'll notice, I'll try and pull out a pointer that I have some light on. Yeah. One second. Or maybe just, yep, that's right, it'll reflect on this. Science DMZs, i.e., an area where you stick servers outside of all your firewalls, and all they ever pass through are ACLs on your routers. They never touch a firewall. And a quick digression, if data goes through a firewall, it will not reach its potential speed or bandwidth. There's nothing you can do about that, okay? Doesn't matter how much money you spend. If it's being filtered, you will actually make it difficult for your researchers to have high-speed, large data sets pass quickly. So the concept is you put a few servers outside of your firewalls that are well protected, and you allow people to transfer data from there. And that's a whole nother topic, but it's one that we deal with constantly as we build these research education networks. More challenges. Hard to, well-trained network engineers. And the classic problem is as you train people, they get hired away and they leave. So it's a constant process of building capacity. Retaining them, right? It can be hard to find business models that work for a research education network. How do you pay for all this if people don't have very many resources? And sometimes these networks get started with external funding, but then there's no plan for what happens when the funding goes away. So they kind of wither and die. Like I just said there. So usually you need some support of your government, right, to be behind this, to help you build this network so that you can obtain some funding, get some discounts, talk to the commercial providers, and in certain circumstances, maybe provide access to fiber and lower prices. And strong national leadership, which oftentimes involves education as to why you might be interested in building a network like this. Because at first glance, it looks like it's costing you money and maybe you're not getting anything for it. So a few examples of how these challenges have manifested. We talked about campuses that are built for low bandwidth environments, so when you finally get the network, it doesn't look very good. Import duties, so maybe you can get your government, your ministry to help remove some of those. Complexity of getting items out of customs, that can be hard sometimes. And then use of wireless and how hard it can be used to use that. In some cases, we run across that as well, especially for point-to-point links. This is a big one, when networks are built by third-party contractors and then they leave and you don't have anybody locally who knows how to fix it, and it's expensive. And then some of the old school practices, such as where firewalls go, buying appliances that actually don't scale and are extremely expensive once you get good connectivity, how you build your wireless network, that kind of stuff. Shaping your traffic, etc. So these are things that we run into, and basically we do a lot of capacity building, workshops like we're going to have this week to talk about how you approach these kind of designs. So there's been a few success stories over the years, quite a few, and this is a very small sample set of some of the more successful national RENs that have been built up over the years. I'll just give a few examples here. Bhutan, a big one. So there's a national fiber network in place, and the REN got a pair on the backbone across the country, which is what has allowed the network to be built, Druk REN. And that was a government initiative, right? There was not money to do this. This had to be something the government said, as you build out your national fiber backbone, you will